Thank you very much, Tim. I fear that I'm the medicine after the spoonful of sugar this morning. But before we launch into the details, let me give you a brief overview of what I'm aiming for. I'm going to tell you about scarf lemma, and the title I gave to the two sessions was Scarf Lemma and Applications. And the applications are all to matching. And there are two reasons for this. Reason number one is matching is a subject of great current interest among economic theorists. And second, matching is a subject that has attracted the attention of computer scientists and economic theorists and operations researchers for at least 50 years. If anything is an example of a successful collaboration, it is the study of matching. And what is interesting about this collaboration is that it has not been done through individuals working together, but simply people reading each other's papers. Right? There are two threads in the literature on matching. The first thread I'm going to call cardinal, which is concerned with the problem of finding a matching that maximizes some function. So maximize a weighted sum of edges that form a matching. This problem in economics is known as the Shapley-Shubik assignment game or assignment model, and in computer science it's of course the bipartite matching problem. Okay? As I said, this has a long history. Some of you will recall that Harold Kuhn, who had an algorithm called the Hungarian algorithm, which he would be the first to admit that he was unfortunately anticipated by Seidel a century earlier. Subsequently, Damage, Gale, and Sotomayor showed that the Hungarian algorithm for the assignment model actually terminated in the minimal Valrasian prices, and the minimal Valrasian prices were actually the Vickrey prices for that particular economic environment. Okay? More recently in economics, the Galai-Edmonds decomposition theorem for matching has proved useful in the study of kidney matching. So there's one thread in the matching literature where you see ideas from one subject being moved over into the other. Okay? Now, the other thread in matching theory, I'm going to call ordinal matching. That begins with Gale and Shapley. There, the goal again is to find a matching, but not a matching that optimizes some function of the edges. Rather, you are looking for a matching that is in some sense not dominated by any other matching. Now, the two threads have developed almost independently of each other, but nevertheless, you see many parallel results. Right? So one of the things I want to convey to you is you should not be surprised by this the moment you understand Scarf's lemma. Scarf's lemma, in some sense, gives us an explanation for why we should see roughly the same results in both the cardinal and the ordinal matching literature. The second message I want to get across is that Scarf's lemma provides a different way to look at matching problems that I think is fruitful in the sense that it suggests interesting directions that have not been pursued so far. So those are the two messages that I want to convey both today and tomorrow. Okay? So I'm going to begin first with the statement of Scarf's lemma, and the statement I'm going to give you is not the version that appears in his published paper. It's a version that appears in an unpublished paper, and the first time I learned about this particular interpretation or rendering of Scarf's lemma was in a paper by Kiralyi and Papp. Okay? So here is the essence of the lemma. You have a non-negative matrix and a vector of right-hand sides, and every component of the vector of right-hand sides is strictly positive. Okay? And you have a polyhedron. Here's the polyhedron. Okay? Now comes the peculiar part. Every row of the matrix has a strict preference ordering over the non-zero entries in that row. If you want, you can imagine every entry of the A matrix is positive, in which case every row has a strict ordering over the columns. Now, why on earth such a feature should be interesting is not clear at first glance, but bear with me. Okay? Now, a feasible vector x in the polyhedron dominates a column if the following is true. There is a binding constraint, I. Okay. That column has a non-zero intersection with that row. And if you ask that row prefers every column that intersects it and has positive weight in X to column R. So in terms of a picture, here's the matrix A. Here are the components of the vector x1, x2 up to xn. Here is a row I. Here is xr. So xr has a non-zero entry here in this row. If you look at all the other non-zero entries in that row that have positive weight in X, that row prefers every one of these to this one. Okay. Let me pause here for questions. Yes?
So there's only one such one of these.
So you fix an X, okay? That vector X dominates column R.
There's only one R.
There's only one R, right. Okay. Now what you can do is you can ask, is there a vector X that dominates every column R? So can you find a feasible X that dominates every single column?
You just said there's only one such column.
No.
Hypothesis is
Here I'm defining dominating a single column. Right? This is the definition of X dominating column R. Now I can ask, does there exist an X that dominates every column?
Oh, I see. R is not necessarily positive, and XR is not greater than 0.
Yes. XR could be 0. I'm not saying XR is positive or not. Just pick any column R, and domination should say that you should prefer everything that achieves positive weight to column R. Strictly. And if column R gets positive weight, then it's...
Different indices I for different columns, probably, I'm guessing.
I'm sorry, yes. So for every column R, there exists an I.
Okay.
Right.
So if X is the old zero vector,
Yes?
what happens then?
If X is the... Okay. I can kill that by requiring this to be equal to. Yeah. Okay. The reason why I didn't bother about it is because here is Scarf's lemma. Every such polyhedron has an extreme point that dominates every column of A.
Doesn't B strictly positive? Because you have to have a row where the constraint is binding. Can B is strictly positive?
Yes, every component of B is strictly positive.
So X can't be the zero vector?
Yeah, X can't be the zero vector. Yeah. Right. No, but that's, as I said, if you want, set it equal to, and that immediately kills the concern with 0. Yes?
Is there like some special case, like for example, if A is a 0, 1 matrix?
I'm going to give you an example in a moment. As I said, as stated, it is not clear that this is relevant for anything in particular. Okay? Okay. Okay. So, okay. So to make sense of what's going on here, it's useful to look at an example. But before I do the example, here's a way that you can anticipate what's going on. Think of each row of A as being associated with some agent. And each column of A represents a coalition of agents engaged in some activity. And the entry Aij represents, in some sense, the contribution of agent I to activity J. Okay? And then this ordering you can interpret as a preference ordering of the agent over the different coalitions it could belong to, as well as the levels of activities that it would be associated with. Okay? So let me give you an example, and the example I'm going to give you is the proof of the existence of a stable matching in the sense of Gale and Shapley. Okay? So we have a complete bipartite graph. here are the two sets of vertices that I'm going to call doctors and hospitals. And each hospital has a capacity of 1, so every hospital can admit only 1 doctor. I'll assume that all edges are present, and I will assume that you have the same number of doctors as you do hospitals. This is without loss of generality by adding dummy doctors and dummy hospitals. For any vertex V, now what's a vertex? A vertex is either an individual doctor or a hospital. Delta of V is the subset of edges incident to vertex V. Right? And every vertex has a strict ordering over the edges that are incident to it. But since this is a bipartite graph, if I'm a doctor and this is one of my incident edges, that incident edge goes to a particular hospital. So a preference ordering over my incident edges is also a preference ordering over the hospitals. And the same is true for each hospital. Okay? Now, what are we interested in? We're interested in a matching that has a certain property. So let me first describe matchings. Introduce a variable x sub e is 1. If you select the edge, what is an edge? An edge is a doctor-hospital pair and 0 otherwise. And the convex hull of all feasible matchings we know is given by this. So you can either invoke the Birkhoff-von Neumann theorem, or you can invoke total unimodularity of this constraint matrix. This is getting to your example later. Okay? So what does this constraint say? The set of the number of edges that I pick that are incident to vertex V is at most 1. So every doctor is matched to at most 1 hospital. Every hospital is matched to at most 1 doctor. Now, a matching is blocked by a pair, DH, if first of all you didn't match that pair, and if you look at Dr. D is currently matched to H prime. Dr. D would prefer hospital H, and if you look at hospital H, it is currently matched to Dr. D prime. Hospital H would prefer Dr. D. So in other words, this pair is a blocking pair if each of them, by breaking the matching that you have assigned them, could do better. Both of them must do strictly better. Right? Now, the idea of blocking here is capturing the following notion that agents can vote with their feet. You can dictate a matching, but you cannot force agents to accept the matching. And the way we're modeling that idea that you cannot force them to accept a matching is through the notion of blocking. So any matching you propose must have the feature that it cannot be blocked. A matching is called stable if it cannot be blocked by any pair. Okay? Now, it is not immediately obvious that stable matchings exist. The other thing I'd like you to notice is that this is not an optimization notion. Stability is not obtained by maximizing some function of the edges. This is an ordinal notion of matching. Now, there's a remarkable result of Gale and Shapley that gives us a very simple algorithm to find a stable matching always, so they always exist. And what's more than one of these can exist. Everyone with me so far? So I'm going to use Scarf's lemma to show you the existence of a stable matching. Here's the polyhedron that describes all matchings. So this is the A matrix, that's the right-hand sides of B's. Everything is strictly positive. The coefficients of the A matrix are either 0 or 1. So the first condition in Scarf's lemma is met. Every row of this AX less than or equal to B matrix corresponds to either a doctor or a hospital. Every doctor or hospital has a strict ordering over the edges, but edges correspond to variables which correspond to columns of the A matrix. So every row of my A matrix here has a strict ordering over the columns that intersect it. Now, what does it mean for vector x that satisfies this to dominate a column? Well, here it is. Let's boil this down to the case of matchings. For every edge E, for every column, there exists a row. A row in our case is a vertex, which is either doctor or hospital. That edge must be incident to a vertex. So there exists a vertex in which positive weight is assigned to everything at the same rank as E or higher. Binding constraint. Now, what do we know about the bipartite matching problem? Every one of its extreme points is integral. Scarf's lemma says there exists a dominating extreme point. So therefore, there exists a matching. This is all 0, 1. So in particular, if edge E were not chosen by your matching, that would be 0. And what would that say? It would say that vertex V is matched to at least one edge that it prefers to edge E. So edge E cannot be part of a blocking pair.
F is either a doctor or a hospital, so that's...
So there exists a vertex V. I didn't specify whether it was doctor or hospital, but if you want, take it to be doctor or hospital. Yes, Eva?
So what does this say in non-bipartite matching?
Next few slides.
Oh, sorry.
Yeah.
Is this rehearsed or...
We read each other's minds. Okay. Now, no algorithm, just existence. Okay. What does this particular example...
Scarf's lemma give you an algorithm?
It does give you an algorithm. You may not like the algorithm.
Is it different? Is it different?
It will be different, and I'll get to that in a moment also. If I go back to Scarf's lemma, in a sense, what Scarf's lemma tells us is the following. Every property of an extreme point of this polyhedron is inherited by the dominating extreme point. That's the connection between cardinal and ordinal matching. Every property of the extreme point of your polyhedron must be inherited by the dominating extreme point. Right? Any property that is true of your extreme point has to be true of the dominating extreme point.
Just because it's a subclass.
Just because it's a subclass. That's exactly right. Okay? But it's that observation that then allows us to say something about the non-bipartite case, which I'll get to in a moment. Okay? Okay. Non-bipartite case. So the non-bipartite case is called the stable roommates. So now I simply have a set of vertices. I have a set of edges. And again, delta V is the set of edges incident to vertex V. And every vertex has a strict ordering over the incident edges. But once again, every edge links to another vertex, so a strict ordering over the edges is a strict ordering over the other individuals in the economy.
So people can be linked to more than one person? I first had a problem.
Well, so you can have multiple edges. So I have for every possible pair that could be matched, I insert an edge. But you will only be matched to one other person.
I understand the rooming situation.
Right. Okay. So again, let x equal 1 if we select edge E and 0 otherwise. The integer points of this polyhedron will correspond to matchings. Now notice I did not say that the extreme points of this polyhedron are integral. That's not true. That's only true for the bipartite case. Okay? But what do we know? Well, let me complete by saying what we mean by stability here. It's the same idea. Fix a matching. Now look at an edge that is not in your matching. XE is 0. This edge forms a blocking pair if the members of that pair would prefer to be with each other than who you have assigned them to. So it's exactly the same definition. If you notice, the notation has not changed at all. The only thing that has changed is the polyhedron. Well, what do we know about the extreme points of this polyhedron? old theorem of Belinsky's and independently Nemhauser and Trotter. Every extreme point of this polyhedron is half fractional. So every variable is either 0, 1, or a half. What else do we know? If a variable takes a value of half in one extreme point, it takes the value of a half in every extreme point. What else do we know about this polyhedron? The variables that have the value of a half lie on odd cycles. Okay. Now, here is where I'm using properties of the extreme point that are going to allow me to say something about the nature of the stable roommates problem. Okay. Let me define what's called a stable partition. It's a subset of edges. Every component of that subset of edges is either a single edge or an odd cycle. Okay. Each cycle has the following property. So a picture may be better than what you have here. So V1 prefers E2 to E1. So V1 prefers this edge to this edge. In other words, Mr. 1 prefers Mr. 2 to Mr. 3. Mr. 2 prefers edge 3 to edge 2. So Mr. 2 prefers this edge to this one. In other words, Mr. 2 prefers Mr. 3 to Mr. 1. And then finally, over here, Mr. 3 prefers Mr. 1 to Mr. 2. For those of you familiar with the stable roommates problem, this is the smallest counterexample to the existence of a stable roommate solution, this cyclic preferences. Okay, I'm going to call this an odd preference cycle. Okay. And finally, what do I need for a stable partition? For every edge that is not part of the partition, there exists a vertex covered by the partition that is incident to edge E, and that vertex is incident to an edge that it prefers to E. So every vertex is covered by an edge in the stable partition that it prefers to any edge not in the partition. Scarce lemma, stable partitions exist.
Why is that? Why?
Every extreme point is 0, 1, half. The variables of a half lie on odd cycles. And then everything else comes from the domination condition. Okay. Now, we can now ask, what's special about the variables that take the value half? Well, the variables that take the value half lie precisely on these odd preference cycles. Why is that? Let's look at this. If this has value half, then there must be an edge that vertex V prefers to edge E that also has value half. So I've got one edge with value half and point it in the direction that, so I've got edge E. And edge and vertex V prefers, okay, so here's edge E, here's edge F, sorry. Half, half. But if this has value a half, again, by the dominating condition, there must be another edge coming out with value a half, call that G. But the variables with value a half can only lie on odd cycles. But those odd cycles have to precisely be odd preference cycles by the domination condition. So we now have a classical theorem of Tan's. Stable roommate solutions exist if and only if there are no odd preference cycles. Okay. So two important results in stable matching, and we haven't even broken a sweat yet. Everyone with me so far? Okay. So this is what I meant earlier by, because you inherit the properties of the extreme point of that polyhedron, if that polyhedron has very nice properties, you can exploit those properties in thinking about stability. Yes?
What happens if I put in the subset condition to make the vertices matchings, actually?
Okay, very good. So one of the things I didn't mention in the history of sort of the connections between computer science and economics and the study of matching, the version you're now asking for is sort of hypergraph matching, right?
No, I'm asking regular matching. I want to put in the condition that on an odd subset of 2k plus 1 nodes, only 2k edges can get matched, which makes the vertices match.
Very good. So you can write down such a theorem in this case. You do not need to impose the odd cycle constraint on every odd cycle. You only need to impose it on the odd preference cycles. Then the theorem you get is that if that has an integer solution, a stable roommate solution exists, and if it doesn't, then there is no stable roommate solution.
Maybe I should take this offline, but I'm asking a version that's guaranteed to have matching, all the matchings as its vertices.
Yes.
And I wonder what the quality would mean for that version.
Now I understand the question. You want to add in extra constraints.
Exactly.
Okay. Now remember, Scarf's lemma requires that every constraint have an ordering over the columns in it. So if you try to add in extra constraints, what's the natural ordering to impose? Okay? But it's a good question to ask, because I think this, because I think in some sense, if I think about open questions, which I'll talk about tomorrow, that Scarf's lemma raises, one of these is I think Scarf's lemma provides a useful way to think about matching with side constraints, if you can be imaginative about how to choose the preference orderings over the side constraints. And there are some instances that my co-author Tan Nguyen and myself, we think we can do. So we can think of some simple examples where it's easy to do. The challenge now is, are there more interesting examples where this can be done? Okay. Now, if you ever take a class in matching in an economics department, you will run through stable matchings, maybe stable roommates. And there's a separate class of problems which are sometimes called house allocation problems. The most famous of these is the house allocation problem of, I think the original paper is Scarf-Shapley with a beautiful algorithm due to David Gale known as the top trading cycle. Here is the problem. Every agent owns a home. Every agent has a strict preference ordering over the homes, including, over others. Okay? Is there a way to assign homes to agents in such a way that no subset of agents, by walking away and trading among themselves, can each do strictly better? So as I said, there's a beautiful algorithm of David Gale's called top trading, which finds such an allocation. And this is usually treated as being separate from the stable matching problem. There is a more general version of this problem, which I want to describe, which I'm going to call the Kanzi housing model after Martin Kanzi. So you have a set of agents. Some of them own homes. Not everyone has to. The ones that don't own a home, you can give them a dummy house. Each agent also has some money, and the utility of an agent I for a monetary amount Y and a house HJ is denoted by this. And the only thing you need on this utility function is it should be continuous and non-decreasing in money, holding house fixed. Now, in the case when there is no money, then you only have utility for house. You have the Scarf-Shapley housing model. In the case where your utility for a house and money is the utility of the house minus money, and you have an unlimited amount of money, you have the Shapley-Shubik assignment model. Okay? So this captures all of the main housing models into a single model. And the question one asks is, in this model, does a core exist? Once again, is there an assignment of homes to agents and monetary transfers so that no subset of agents has an incentive to block the allocation by walking away with their endowment and trading among themselves? Existence follows almost directly from Scarf's lemma. So Scarf's lemma gives you a single machine to give you existence results for all of these problems. Okay? Everyone with me so far? Okay. I was going to talk about cooperative games, so let me skip that. Yes.
Is the problem you described, is it convex? Is it solvable? The Kinsey-Hausen?
Okay, so this boils down to what's the complexity of finding the dominating extreme point in Scarf's lemma.
Oh, right. So it's as hard as that?
Yes, it's as hard as that, right. Yes, okay. Yes, okay. So you could now ask, what is the complexity of finding the dominating extreme point? It's p-pad complete. Now, I know that computer scientists are frequently nervous about computing. Economists are not. So I urge you to be fearless. So there are two things I would say here. One, the stable matching problem tells you that there must be instances of Scarf's lemma where finding the dominating extreme point can be done in polynomial time. Natural question, what other instances are there? Okay. Second, even though it is p-pad complete, Peter Biro and I think it's Gusfield or Irving in Glasgow have actually run Scarf's lemma for stable matching problems with couples that I'm going to describe in a moment. And they claim on their test problems, now everything is going to depend on what you think their test problems are like, that it runs reasonably fast. And so they ran problems on the order of something like a couple of 100 doctors and roughly an order of magnitude less of hospitals. And these are not problems that you necessarily have to run many times. You're just going to run them once. And people are not, waiting with bated breath for the solutions. So I don't think for certain reasonable sizes, I don't think the computations are that involved.
So the same thing is said about Lemke-Hausen, right?
The same thing is said about Lemke-Hausen, right? So, yeah, okay. Now, Scarf's lemma, in a sense, you should expect this, given the fact that you can use Scarf's lemma to get all these various existence results. So, for example, when you'd asked me the question earlier, I'd asked about I'd said hypergraph matching. Well, it turns out that about roughly 15 years after Scarf, Lovash independently rediscovered the lemma. It's in his paper on normal hypergraphs and the perfect graph conjecture. So there are actually a number of recent applications of Scarf's lemma in computer science. So the one I mentioned by Lovash is an old one. A more recent one is by Penny Haxel, in which she models the problem associated with the BGP routing protocol as what's known as the stable paths problem. And then she uses Scarf's lemma to show the existence of a stable path. Okay? There are other more recent applications due to Thomas Fleiner and Ronald Aharoni, where they use Scarf's lemma to show the existence, establish kernel solvability of certain hypergraphs. So it's a very powerful theorem, and so you should expect that it probably has to be in a much higher complexity class than linear programming, for example. Okay. Now, what I've done so far is describe problems for which we knew there were solutions already. And so Scarf's lemma gives us a sort of direct way to get those solutions. Does Scarf's lemma allow us to do anything new? Okay. So this is what I want to go to next. So what I want to go to next is now the stable matching problem with couples. Okay. So here's the setup. I have a set of single doctors and a set of couples of doctors. Each couple is denoted by a pair, first female, second male. This does not represent my views on marriage. This is simply a convenient way to specify an ordering. You'll see why in a moment. D star is the list of individual doctors. Okay. There is a set of hospitals. Every single doctor is characterized by a strict preference ordering over hospitals and the empty set. So the empty set corresponds to being matched with yourself, in other words, not being assigned to any hospital. Right? Every couple has a strict preference ordering over pairs of hospitals. Okay? So what I want to emphasize about this is you're taking the position of not being a marriage counselor. So each member of the couple may have their own particular preferences. That is not your concern. When they come to the mechanism, they have to report an ordering over pairs of hospitals. Okay. Each hospital has a capacity, and the preferences of a hospital are modeled by a choice function. What is a choice function? A choice function takes as input a subset of individual doctors and outputs a subset of that subset. And the choice function we're going to use, which is standard in the literature, has the property of being responsive. And that's another way of saying there's a simple algorithmic description of this choice function. It is this. Every hospital assigns a priority ordering, strict, over individual doctors. So each doctor by themselves gets a score. When you give a hospital a subset of doctors to choose from, it chooses the highest score doctors up to its capacity.
You mean D star here?
I mean, sorry, this should be D star, thank you. The set of individual doctors, not single doctors. Okay, so is it clear what a responsive choice function is? Every individual doctor gets a score. If you give me a subset of doctors to choose from, I rank order them by the score, and I keep picking until I hit my capacity constraint. Now, there is an asymmetry that I want to draw your attention to. Preferences of doctors are described by preference orderings. Preferences by hospitals are described by choice functions. Choice functions are not preference orderings. Every preference ordering gives rise to a choice function. Choose your K most preferred doctors from the set. But every choice function does not give rise to a preference ordering. If I just hand you a choice function, you may not be able to recover an underlying preference ordering. Everyone with me on the distinction? Now, there are two reasons for why you might want to model hospitals using choice functions. Reason one is high-minded. Reason number two is cynical. So let me do the high-minded reason. Yes?
Why can't you extract the order from the choice function?
Okay. The problem is that from a choice function, you can extract whether I rank A over B. But if you just know the pairwise orderings, that's not enough to get the ordering over everything. You might say, well, what if I choose from triples? But the problem is when I choose from the triple, you're missing information about one pair. Is that? Okay.
You can construct a preference ordering over subsets of doctors. How much was it?
No, you can't. No, so if I give you a choice function, it need not be consistent with a preference ordering over subsets. Yes?
If your choice function is responsive.
If your choice function is responsive, because I'm giving you the extra information, right? Okay. Now, so the high-minded reason is that hospitals simply are simply unable to give you a preference ordering over subsets of doctors because decisions are made by committee. And so perhaps all they can really give you is their algorithm for deciding. Right? So that's the high-minded reason. The cynical reason is the following. Gale and Shapley's deferred acceptance algorithm. Okay. So, as I told you earlier, Gale and Shapley established the existence of stable matchings with a beautiful algorithm called deferred acceptance, which William Thompson argues cogently should really be relabeled immediate rejection. Let me remind you of how the algorithm works. Every doctor points to their favorite hospital. Every hospital that has at least two doctors pointing to it rejects all but their most preferred doctors. Rejection is irrevocable. I do not get to revisit any doctor I have rejected. Okay. Now think about trying to extend that to the case of matching not one doctor, but many doctors to a particular hospital. This is an algorithm that works in rounds. When I reject a doctor in round K, I may not revisit that decision in round K plus 1. In some sense, my preferences have to have some kind of path independence or memoryless property in order for such an algorithm to terminate in a stable matching. Okay. So if you are locked into the deferred acceptance algorithm, and you want to extend the Gale and Shapley result from one-to-one to one-to-many matching, then you have to think of choice functions which have the right memoryless property. That puts a constraint on the kinds of choices you can look at. What I want to argue is that Scarf's lemma does not constrain us in this way. In other words, there are examples of choice functions that do not have this appropriate path independence property for which Scarf's lemma will give us the existence of a stable matching.
I'm sorry, I missed the punchline for the hospital
For the hospital, right? So it is standard in the literature to model the preference of hospitals using choice functions. And all of the positive results we have about many-to-one matching impose a very strong condition on the choice function, which amounts to path independence.
Was I wrong that the couple's problem is intractable?
It is, and I'm going to describe, and now I'm going to say why this problem is interesting, precisely because it's hard. Okay?
Stability condition with respect to...
I will, very good. I will give you the stability condition for what matching means in this case. But what I want to emphasize here is that Scarf's lemma potentially allows us a way to think about matching problems without relying on the usual assumptions on choice functions. Okay? Okay. Let me tell you what a stable matching is in this setting. So I'm going to use the economic notation rather than the more natural integer programming notation for the moment. So a matching is a function that maps doctors to hospitals. So mu sub h is the subset of doctors that are matched to hospital H. Mu sub s is the position that single doctor S receives. And mu fc and mu mc are the positions that the female and male member of the couple C obtain. Now, what does blocking mean? The first condition you want is individual rationality. So for the doctors, it basically means that whatever you give them should be preferable to the empty set. Okay. For a hospital, it means the following. If I assign this hospital this subset of doctors, and then I hand them that subset of doctors and ask them, choose which doctors you want, they should come back and say, I want exactly the subset you handed me. Okay. Now, what does blocking mean? So there are three ways that blocking can occur. The first is the usual way I've described before with a single doctor. So there is a single doctor that prefers hospital H to the hospital that you have assigned her to. And if that single doctor approaches hospital H and says, consider me along with the doctors you have already been assigned, this hospital says, I will certainly choose you. Okay? Now, the other wrinkle involves couples, and it works pretty much the same way. You could have a couple and two different hospitals, or you could have a couple and two slots in the same hospital. So this is blocking. Everyone with me so far? Okay. So the question is, can you find a matching that is stable? In other words, a matching that cannot be blocked. Okay. So here's an example to show you that stable matchings need not exist. What do I want to draw your attention to in this example? One, it's small. 2 hospitals, 1 couple, 1 single doctor. Second, each hospital has a capacity of 1. So the distinction between choice function and preferences is irrelevant. This is a counterexample to both setups. Okay, now the complexity question. Given an instance of a matching problem with couples, finding if it has a stable matching, that's an NP-hard problem. Roth and Perenson proposed a modification of the Gale-Shapley algorithm, which has the following property. In every recorded instance of the National Resident Matching Program, it has found a matching that is stable with respect to reported preferences. Now, separately, Kojima, Patak, and Roth, Ashlagi, Braverman, and Hasidim have attempted to explain why this may be the case, and this is in a probabilistic model. So preferences are drawn uniformly at random, size of the market goes to infinity, fractions of couples goes to 0. Then the result is that with probability approaching 1, Roth and Perenson will terminate in a matching that is stable. Okay? You seem puzzled, Drew.
Thinking about 1 couple couple, one hospital, since there's non-existence issues even then, if the hospital will only hire both of them, but the couple would rather be unemployed, then only one. So aren't there even just one hospital, one couple counterexamples to stable matching?
Yeah, there might be even smaller counterexamples. I decided to give the first one that I was aware of in published form. Okay. What else do we know? In the US, the fraction of couples is as much as 10%, and the Ashlagi et al. Paper, and Itai is here and you can ask him for more details, shows that if the fraction of couples does not go to 0, the probability of the algorithm not terminating in a stable matching is positive. And simulations by Biro et al. Show that when the number of couples is large, the Roth and Perenson algorithm fails to find a stable match. Okay? So what I've described now is a matching problem where it's NP hard to find out even if there is a stable matching. And second, this is if a stable matching doesn't exist, what are you going to do? So here is a theorem. Given any instance of a matching problem with couples, there is a nearby instance that is guaranteed to have a stable matching. Now, what does nearby mean? For any capacity vector of your instance, there exists a nearby capacity vector K prime that has the following properties. Hospital by hospital, it differs from the original capacities by at most 4. In aggregate, the total capacity on the K prime is no more than 9 more than the original. What's special about K prime? We will give you a stable matching with respect to K prime. We do not change preferences. We do change capacities.
Ricky,
Yes.
K prime can actually be smaller than K?
Yep. In fact, I'm going to stop here and let you ask questions, because if you don't find this result interesting, everything else I have to say is completely irrelevant. Yes?
I have 2 questions. One is, can you find that nearby stable matching efficiently? Second, this result is for what you call responsive preferences?
Yes. So it's exactly for what I think of as the standard setup, responsive preferences on the side of the hospitals, and no restriction on the preferences on the side of doctors. Now, we can actually relax the responsive preference condition and allow a little bit of complementarity and get the same result. Yes?
Can I ask my question in a question form?
Yes.
Do you know anything if I insist that K prime has to be bigger or equal to K?
We don't, but in reflecting upon the techniques used, we think in other words, I think we could get you the answer. I don't know the answer.
And the computation?
The complexity? Yeah. Okay. These were not the questions I was expecting. The question I was expecting was, how do you know these are big numbers or small numbers? But the complexity is, okay, 4 and 9. They look small.
This is not your econ.
This is not the econ audience. Okay. So, yes, Amos.
It seems that whatever the input is, you can generate a case where most of the hospitals, or a lot of hospitals, have to change their capacities. Just repeat the instance multiple times.
Hold on one sec. Okay, so you are exactly right that one should be a little suspicious initially about this result, because think about the counterexample to non-existence I gave you. Why not just duplicate that non-existence counterexample 1,000,000 times? Right? Then it would seem that in each one of those instances you'd have to add extra capacity to be able to get a stable matching. But that's not what's happening. Right? In total, we're adding no more than 9 more slots. So what's really happening is we're shuffling capacity between hospitals. So I may be taking capacity from one hospital and giving it to another, which is why I want the freedom over here to be less than. Okay? Now, if you're bothered by that...
So the thing is, I think I asked this from your co-author and,
yes.
and more convinced, he was more convinced that you can do it going upwards only, with a little bit bigger numbers.
Yeah, so if you insist that I never decrease the capacity of any individual hospital, you're going to have to pay for it by having a larger upper bound here.
But I think Ted was claiming that's a number, not no n.
Yeah, it's a number. It'll be a fixed constant. It'll be, yes. So let me emphasize here, 9 and 4 are completely independent of the size of the problem. This is not an asymptotic result.
What's a typical KH?
Typical KH is probably, the smallest is probably around 20. Okay. Another question you might ask is, how much does a residency slot cost? It's about 100,000 under current estimates. U.S. government spends on the order of $9 billion on the residency program. So Samir Kula suggested that we should actually title this paper, $1 million is enough to solve the two-body problem. Sorry, what's the sum of the capacities? For the typical sum of the capacities. So let's see. I think if we have about
that's all the residents in the U.S., right?
yeah, roughly all the residents in the U.S. So on the order of about 30,000. Yes.
Can you improve on the constants 4 and 9?
Okay. Well, the thing you should be concerned about is that a perturbation of size 4 could be very costly for a small program rather than a big program, right? So if that's the case, you might want a smaller bound here. So the answer is, if you don't like 4, I can give you 3, but then you have to give up on this.
Sorry, what does it mean to give up on that? You get a bigger constant.
I don't think we can bound this. If you insist that this is less than 3, we cannot bound the aggregate increase in capacity.
You cannot bound it, or it's yourself, or there is no bound?
I think the answer is there is no. No, there is no bound. I think we can construct an example where the aggregate capacity could be arbitrarily large. Yes?
How difficult is it to find the K prime?
Okay. So I'm looking at the clock because I want to say stay tuned for tomorrow. Okay.
So do you use Gauss lemma to get
yes. So let me give you an overview of what's going to happen. Yeah, go ahead. You're not happy with the preference model yet?
So if you have responsive preferences, I can still prefer to have at most 10 positions in responsive preferences, and then if you increase my capacity to 12, I might not hire anybody else because I still prefer to have 10 positions.
But notice we never decrease the total capacity. So if there is excess demand for doctors, we're not burning any slots. So if there's excess demand on the part of doctors, we're not achieving stability by burning slots. Right? A trivial way to get stability is get rid of all slots. Right? So we're not doing that. Yes?
You said you thought you could do this, even if you demand that the capacity never decreases?
Yes.
And then you also said that it worked by not eliminating or adding, not eliminating or adding slots possible, but shuffling them around?
Shuffling them around, right. So we'd have to add more in the aggregate.
Yeah, I'm wondering, reduce total capacity, because I was wondering about what you said earlier about what happens if you repeat the same example a million times.
So if you repeat the same example a million times, you might think that should give us a counterexample to the second bound, right? Because you might have to add an additional slot for each counterexample. But we're avoiding that by shuffling capacity between the counterexamples. Right? So you take away capacity from some hospitals and give it to others.
I thought you said earlier, that you can do it by without reducing capacity in any hospital.
No, reducing aggregate capacity.
Okay.
Right. Yes?
Can you do it with a ratio form of bound 1?
Okay. So those of you familiar, for example, with the early paper, say by Tados and Schmois on the generalized assignment problem, where you get a result that says if you allow us to violate the budget constraint by a factor of 2, then we can get you close to the original objective function value. That's a multiplicative bound, factor of 2. I'm going to argue that multiplicative bounds here, these are hard to interpret. I know how to interpret 1, 2, 3 doctors because it corresponds to a tangible monetary amount. 100,000, 200,000, 300,000. I can look at the number of doctors and compare it with the existing capacity of the hospital and get a sense of whether that's big or small. Multiplicative for me is harder to interpret in this context. Okay? But there is nothing to prevent you from doing this kind of analysis and focusing on multiplicative bounds. Yes?
Do you have an upper one with the total number of shuffles?
Good question. No, we don't. We're currently running simulations, and we would like to do the simulations presumably would be to check for 2 things. Is it the large or the small hospitals that are affected? If it's the small hospitals that are affected, this is bad news for us. Right? If there are a lot of shuffles, this is also bad news for us. Okay. But this we cannot tell analytically. Simulation. Yes?
Did I interpret your comment on duplicating the same environment many times correctly? It would seem that that implies that statement 2 can be changed to be the inequality opposite direction with -9. So in other words, you can do the same thing, but only lowering the total number of doctors by -9. Because if you want to do this, you have to have plus and some, minus the other, you have to all balance out.
Yeah, so if you are willing to accept a reduction in the total capacity, I think we can give you a smaller number here, not 9, but something less. I don't know what that is. We didn't do that because the concern you would have is if we were reducing capacity, you might then say, oh, I see how you're getting stability. You're getting stability by removing resources. Right? And so we don't want to do that.
But the
Yes?
point is that construction that does this duplication thing would have to then be using analogous.
On both the upper and the lower bound, yes. Yeah.
How about the strategic consideration?
Okay. The strategic considerations. Well, so my answer is going to be the following. The Roth and Perenson algorithm, which is in use, does not have any incentive compatibility guarantee. So don't hold me to one as well.
But there are no degrees to this. So is there an obvious way to be?
There is, okay. So the strategic concern you should have here, I think, is the following. We're manipulating capacities. In the standard model, we're only concerned with manipulation of preferences. But the question of manipulating capacities has been considered. And in the standard Gale-Shapley model, if agents can manipulate capacities, then you cannot get incentive compatibility. So we're manipulating capacities here, so you might be concerned that hospitals would have an incentive to misreport their capacities because they know when you run the algorithm, the capacities will be adjusted afterwards. Okay? I'm not so concerned about that because hospitals are required to provide a plan justifying their capacities. It's not simply a matter of reporting the capacities. Okay? Now, in terms of the preferences, well, I'll give you the outline of the algorithm, and you can decide whether agents are perspicacious enough to be able to see how to game it. I don't think so. But it doesn't mean that they should report truthfully. Right? But notice I said Roth and Perenson was stable with respect to reported preferences. I didn't say with respect to true preferences. Right? Yes?
Simulations by Hero and those negative results, land simulations on preferences. What happens if you simulate the capacities and you can show that the instances, maybe you can show that the instances that it doesn't exist is really a small measure.
So in fact, in our simulations, we are varying both preferences and capacities.
And you're still getting...
Well, so we don't have the results yet. These are simulations that we're doing currently.
That's a little bit, this theorem motivates kind of maybe in existence is a small...
Yeah, so what this theorem suggests, so this suggests, I think, another theorem that maybe take any instance of a stable matching problem, then with high probability in a small neighborhood around that instance, there must be an instance which does have a stable matching. I don't know how to prove that, but I think this is what this suggests. Okay, so yes.
Is there a clear connection between how preferred the hospitals are and how the capacities are adjusted?
No. So in the way that we've set up the algorithm, we do not favor one hospital over the other, but there are various places that you could break ties in a particular way so that you could break ties so as to avoid touching the small capacity hospitals as late as possible in the algorithm. Okay. Let me let me in the one, I've run over here, but in 1 minute, let me tell you what you should expect to see tomorrow. I'm going to set up the problem of finding a matching as a linear program so that I can use SCARF. Now here's the other feature of SCARF. SCARF gives us a definition of stability for fractional matchings. I'm going to take the fractional matching, which is the dominating extreme point in SCARF, and I'm going to round it into an integer solution in such a way as to preserve stability. Now, that rounding idea actually goes back to the Shapley-Folkman-Starr lemma. So the other thing I will tell you about is the Shapley-Folkman-Starr lemma and the refinements subsequently in computer science to that lemma, which give you much stronger bounds than the original Shapley-Folkman-Starr lemma does. Okay? So I've exceeded my time. I apologize for running over. I'll see you all tomorrow.